Hi Year 12, this is our second lesson for the topic of further integration for Extension 2 Mathematics. In this lesson we're going to look at T-ratio substitutions. So far this topic we've learnt about trigonometric integrals, composite functions, substitutions, inverse trig functions, and completing the square. Now remember, a rational function can be written as the ratio of two polynomial functions. So here we have f of x is equal to p of x divided by q of x. And of course, q of x cannot equal 0. When we're integrating a rational function that contains sin x or cos x, one method is to substitute using t-ratios. One of the things you're going to have to do in this topic is recognize the different integrals and match the appropriate method. So here's t-ratios. The substitution comes from this, t equals tan theta on 2. And if we use this triangle here, and make theta onto the angle, then this side would be t and this side would be 1. Using Pythagoras' theorem, we get the square root of 1 plus t squared on the hypotenuse. Thus we have the following. Sin theta on 2 is equal to t on the square root of 1 plus t squared, and cos theta on 2 will equal 1 over the square root of 1 plus t squared. Now they're not particularly useful. We can't really substitute sin theta on 2 or cos theta on 2. We really need sin theta and cos theta. So we use our double angle formulas. Sin theta is equal to 2 sin theta on 2 cos theta on 2, making those substitutions and tidying up we get sin theta is equal to 2t over 1 plus t squared. Similarly for cos theta, it's equal to cos squared theta on 2 take away sin squared theta on 2. Substituting, we get cos theta equals 1 minus t squared all over 1 plus t squared. And finally, tan theta is equal to sin theta divided by cos theta, which is going to give us 2t over 1 minus t squared. Now, in order to substitute for t, as well as having sin theta, cos theta, and tan theta, we really need an expression for d theta dt. And we're going to get it from t equals tan theta on 2, and we're going to differentiate this. We're going to do dt d theta. So remember, differentiating tan, we get sec squared. This is a chain rule, so we multiply by the derivative of the inner function, which is a half. Gives us a half sec squared theta on 2. But I don't want dt d theta, I want d theta dt, so I'm going to invert both sides. D theta dt is equal to 2 cos squared theta on 2, and substituting, I end up with 2 over 1 plus t squared. So in summary, using t equals tan theta on 2, we have sin theta equals 2t over 1 plus t squared, cos theta equals 1 minus t squared all over 1 plus t squared, tan theta equals 2t all over 1 minus t squared, and d theta is equal to 2 dt all over 1 plus t squared. Now on your reference sheet, you are given sine, cos, and tan in terms of A, but you are not given dA dt. So you've either got to memorize it or you've got to work it out when you need it. Let's look at some examples. Find the integral of 1 on 1 minus sine x dx. Okay, so we need to make some substitutions for sine x and also for dx. And this is what we get. So here we've got 1 take away, there's sine x there, and then multiplied by dx here. Now one thing to be careful with is this dt. It should always go at the end. Okay, don't get sloppy and put it up here or even up here. It is the end point of this whole operation. This means find the integral of all of this with respect to t. Sometimes we do put it on top like here, but that's because this is a single fraction. So in this case, I would tend to put it right at the end. All right, we need to tidy this up. So we'll start with this part. Okay, we need a common denominator. This is going to become 1 plus t squared over 1 plus t squared. And I've got 1 divided by this fraction, so that's the reciprocal. So have a look. The 1 plus t squared's come up the top, and this 1 plus t squared minus 2t stays down the bottom. These two cancel, and that neatly factorizes into a perfect square. And bringing that up the top, I'm ready to integrate. So I get 2, and then t minus 1 to the power of negative 1 divided by negative 1, also divided by the derivative of the second function, which is just 1. I haven't even put that in, plus c. Tidying this up, and this is not the answer. Don't forget to substitute back. So t, we don't want t, we want x. T is tan x on 2. And so there's our final answer. Okay, here's a definite integral. Use the substitution t equals tan theta on 2 to find the exact value of the integral between 0 and pi on 3 of 1 on 1 plus cos theta plus sine theta d theta. Right, so the first thing that we're going to have to do is change those limits. So let's have a look at how we do those. We've got, these are thetas, so theta equals 0 and theta equals pi on 3. So when theta is equal to 0, t is equal to tan 0, which is 0. When theta is equal to pi on 3, t is equal to tan pi on 6, which is 1 on root 3. Okay, we're ready to go. So here's the substitution. Have a look at that. Bit of a mess, isn't it? So we've changed our limits. Here I've got 1 divided by 1 plus, that's cos, plus that's sine, times this is d theta. Right, same thing that I had before. I've got the reciprocal of this fraction that's on the denominator. This is 1 plus t squared over 1 plus t squared. So I end up with this. 1 plus t squared plus 1 minus t squared plus 2t, and then I've got that 1 plus t squared on the numerator. Again, they cancel out, and I end up with 2 over 2 plus 2t, which I can cancel further, and becomes the integral between 0 and 1 on root 3 of 1 over 1 plus t dt, which is just a log, isn't it? And substituting in the 1 on root 3 and the 0, I get this. Ln of 1, of course, is 0, so this is our answer. And there it is. Example 3. Find the integral of sine x, all divided by 1 plus cos x dx. Now this one's subtly different. We've got a trig expression on the numerator as well as the denominator. But before you rush into t-ratio substitutions, take a moment to think. Sine x is the derivative, or mostly the derivative, of the denominator, which means that we can use the reverse chain rule. We do need a negative because the derivative of 1 plus cos x is negative sine x, so let's adjust that. But now all we've got is log, so it's actually equal to negative ln of 1 plus cos x plus c. Last example, integral of 1 divided by 5 plus 4 cos x dx. Okay, we're back to t-ratio substitutions. Can you tell why? Because we don't have the derivative of cos x sitting on the numerator. So we need to make those substitutions. Here we have cos x, and this is dx. Okay, I need to tidy this up, so I need to make a common denominator here by multiplying top and bottom by 1 plus t squared. And then I have got the reciprocal. So we do that all in one go. We've got 5 plus 5t squared plus 4 take 4t squared. I've flipped it upside down, and 1 plus t squared is on the numerator, and they cancel out. Tidying it up, I get the integral of 2 divided by 9 plus t squared dt. And this is not a log because we don't have the derivative of t squared sitting on the numerator. In fact, it's inverse tan. So I'm going to bring the 2 out the front and use my reference sheet, and I'm going to get 2/3 inverse tan of t on 3 plus c. Don't forget to substitute back because we don't want t, we want x. But t is tan of x on 2. It's a bit ugly, but that's actually the answer. Okay, that's it for this lesson. Now next lesson we're going to look at partial fractions.